Okay, good morning, everyone. I think I'll start now. I think a few people are still having breakfast, but I need to dovetail in with the security session that starts here afterwards. So I hope you had a great evening last night and have had time to recover from the drinking, and I hope you're looking forward to the session today. So I think I made a bit of a mistake to agree to talk to you this morning, not in general, but after Mike. So I think a couple of weeks ago, he started waking up to, oh, I've been signed up by Lucy to come to the summit and do a keynote. What shall I talk about? So, you know, Mike, why don't you do something like you did at the APM in August, cover some of the session there. Yeah, that sounds good. So he came back last week. Yeah, that only took me 20 minutes. What do you want me to do for the other 40? And we said, well, you could answer questions from the audience. And he said, no, I'll tell you anecdotes about the background of ARM, and that'll fill up the rest of the time. So he's covered a little bit of the stuff I wanted to do at the start of my talk, but I'll probably take a different track through it. So I'll give you a bit of background of ARM and its two organizations, and then what ARM research is, how it fits with that business. Then talk a bit about our internal structure and our current focuses. Okay, so as you know, ARM Technologies is now a subsidiary of SoftBank. We have about 6,000 staff or so worldwide, and we license a broad range of technologies to our customers, be it processor architectures and implementations, GPUs, systems underpinning that, through to radios. And we're also a software business, so we work extensively with the open source community, with Linaro, contributing back to technologies that influence the ARM ecosystem in terms of, you know, the Linux kernel, OpenSSL, LLVM, and the like. So our fundamental business model is we work with semiconductor partners and their customers, the OEMs, and we talk about the problems that they have. And from that, we develop solutions that we propose, incorporate those into our technologies, and we will then license those to the semiconductor partner. And they'll pay us a license fee, but also for every chip that they manufacture, a royalty. So from that basic model that actually started from the outset of ARM, I'll talk through a couple of examples of how that's worked over time. So as Mike alluded to yesterday, ARM was a spin-out between Acorn and Apple. Acorn had developed an internal homebrew RISC processor to feed their next personal computer, kind of targeted at the education and home markets. And Apple was quite interested in the promise of this processor in terms of its cost, its performance. For their first attempt at a tablet computer, the Newton, notice it came with a pen. So back in the day, the first ARM cache processor had a virtually addressed cache. That has some benefits in terms of cheap implementations, so you don't need to go through the MMU before you kick off the cache accesses and do the tag comparisons. It has some downsides from the OS's point of view in terms of when you do a context switch, you need to do a bit of maintenance there. And from the Newton operating system, Apple were really interested in getting at a low context switch time. So their engineers spoke with ours, and we came up with a better solution where each page of memory could be associated with a domain, and a domain was just a 4-bit integer in the page table. And then on a context switch, you could write one register in the processor to say which domains were accessible from the context that you were going to or not. And in that way, you didn't need to do a bunch of cache maintenance on a context switch, and it made the context switch quicker. So that was probably the first example of what I think is quite deeply enshrined in ARM's DNA of a spirit of collaboration. We like to understand our customers' problems and work out compelling solutions to that. If you go to the pivotal success point for the company, and that's when we got designed into the first GSM phones, again, there were some problems there. We spoke extensively with Texas Instruments and Nokia and understood why they couldn't incorporate our existing processor technology into their devices. So they were really concerned about, firstly, code size. They had thousands of lines of control and UI code in their phone, and the 32-bit fixed instruction word of the early RISC processors was a problem for them. It caused them to need a lot of flash, a lot of memory in their systems, and that added to the expense, which made the proposition of the phone less viable. The other concern they had was, you know, if you go to the BBC Micro there, you had an obvious debug flow. You had a monitor attached to it. You could tap in, find out what was going wrong with your program. on the phone, if it crashed, you got no real good way of accessing that. So we worked with them, and the proposals that went into the 7TDMI core that was used in these phones incorporated our thumb 16-bit encoding to address the code density. Also had a over JTAG debug solution to let you debug, get into, and understand the problems with these deeply embedded systems. So as our success continued, we proliferated the use of ARM into many other domains. And again, we got more opportunities to speak with customers, learn about the problems. In hard drives, for instance, you couldn't use the stopping debug, because if you stop the servo control of the drive head, it will crash into the drive, destroy it instantly. In automotive, you need things like fault-tolerant capabilities, and so on and so forth. So, ARM gets called a closed architecture. I'd say not really. We're really open to understanding problems and incorporating solutions into our technology and working with customers to come up with successful and compelling products for people. Okay, so how did that pan out for us? So in the first 26 years, our partners shipped 100 billion cores, or 100 billion SoCs, and we're now predicting that in the next 4 years, they'll do the same again. And this is like the on-ramp of the Internet of Things. And depending upon who you talk to, some people say 1 trillion by 2035, and whether it's 1 trillion or half a trillion, 35 or 38, doesn't matter too much. The scale of that is huge. So when you talk to a layperson about the Internet of Things, they probably first go to the blue box at the top, harnessing the data, and they got this viewpoint of these trillion connected devices are all pumping their data into the cloud. You're going to crunch that with machine learning and data analytics, and from there you'll unveil some nugget of value and make a fortune and retire early. But actually for the businesses who are trying to make use of IoT technologies, there's a whole raft of problems that they need to solve first. So first of all, you need to procure your device. It may range from an ultra-constrained battery-powered or energy-harvested node all the way through to a connected rich capability node. You then need to be able to connect them together. And again, depending upon the device profile, you'll probably be using different communication standards. After you've got them connected, you want to manage them. And there's a variety of different cloud-based management interfaces to these devices. And it may be that it's provided to you by the device provider on their own cloud, or you might want to host it in an AWS environment yourself, or you might want it on premises because you don't want the data to head outwards. Now, for any decent-sized organization, like a hospital or something, it's unlikely that you'll have procured all of these devices from the same vendor. So actually, it's going to be fragmented. You can have different radio standards, a whole bunch of different terminals to maintain these things, and that sounds like a right management headache for people. And finally, because all of these things are communicating over networks, security is a concern for you. So not just the communication between the device and the cloud, making that secure, but also the fact that the device could be hacked into. How are you going to roll out firmware updates over the cloud robustly? How are you going to detect when something has been compromised? How are you going to bring it back into line or quarantine it when it has been? So once you've done all of those things, then you get to the blue bit. You can then pump the data back and get value from it. So I'm recognized this trend, and we've come up with a stack of what we hope to be quality commodity solutions to allow you to focus really on the business need. And we will deal with a lot of the essential and difficult, but nevertheless not the value distinguishing bits of the business. So be that the connectivity management or device management that existed in Embed already. And around the side we have, in green there, the device security platform or solutions ranging from secure communication protocols to robust and reliable over the firmware update. So as an example, here is Alphatronics. There are several Alphatronics, but this one is a Belgian one. And they are leaders in barrier access control. And we're already working with the French waste management company. And in France, every citizen gets a card, and they get to go into the recycling centers a certain number of times a year. And if they exceed that, they need to start paying. and you get weighed before and after the bin, so you can kind of tell, okay, this much of this class of material was deposited in the bin. And the problem that the waste management company had was not that aspect, but the fact that they were sending their fleet of trucks out to empty bins, and they're finding that some of them were half full. So from that point of view, it's waste of their fleet time. So what Alphatronics came up with was now Smart Bin, and that communicated through GPRS back to the cloud, indicating when the bin needed emptying or not. And this, I think, talks to some of Mike's point of networking is really difficult, maybe some of Lee's points made yesterday in terms of, when you move from performance, there are other ways of ascribing value to your system. So I think the waste management companies know what a bin should be doing, and they're not actually asking for a smart bin, they're asking for a better one. So getting that bin helping out their logistics is good, but if it gets hacked or is unreliable, that's not really helpful. That's not a better bin. Anyhow, the communication channel that Alphatronics chose was GPRS, and they didn't have much experience there. And that was an area where ARM could come in with its embed technology and help out the secure provisioning of this functionality. Okay, so that's a bit of background of two ARM businesses now. So the hardware IP licensing, and then building on top of that, internet services. So where does research fit into that? So we are a corporately funded central part of the organization. We're not affiliated with one business group or the other. We liberate some money from their revenue stream in order to better the future growth of the company. So we have a variety of activities led up here, from identifying what we think the future important trends are going to be, what the important problems are going to be facing the industry and ecosystem. And then we work to prioritize those, and either internally we develop solutions and technologies that we hope to translate and deliver into the product groups, or we may partner externally, and again, for more speculative things, again, see what the solutions may be in the future and which of those can be onboarded and ultimately be incorporated into our business line products. So along with external collaboration, there's an aspect that, there are some things which are more risky, more speculative, and probably the right place to do that, given our finite resources, isn't internally in a relatively small research group, but actually to engage with and make partnerships with the external academic community. And that's where the collaboration programs aspect of the group comes in. Okay, on this slide, these are kind of the key people you may find in research, and a lot of them are here in the summit today. If I could get all but the skill group leads probably to stand up, and I'll quickly point at you. The skill group leads, don't feel let out. There's a slide for you later. But we got lead of the group is Eric Henenhofer. Nigel, did you make it in today? Not sure. Okay, so, but Nigel's not around. We have Chris and Andy somewhere. Wave. Can't see Andy. Okay. They'll all wake up eventually. You saw myself, Greg, and Rob yesterday, so we're three of the fellows in the group. Primarily, we're looking at future trends and trying to motivate kind of grand overall direction for technology in the group. Kim couldn't be with us, so she's based out in Austin, has been doing busy work. Couldn't make it to the summit this year. And then at the front somewhere, we had John Goodenough, lead of the Research Collaborations and Enablement, and Khaled, always dressed smartly in a suit in the middle there. He leads our ARM education team. Okay, so this chart talks through how we enumerate and prioritize the work we do. And most businesses that have a research function end up with something similar. It ends up being a funnel. So there's an infinite number of interesting things we could look at, and there's a finite number of people that we have. And we're also being paid by a business that's interested in growing profits over time. So ultimately, you set up a system where you enumerate problems that you'd be interested in looking at and you think are compelling for the business. And then you need a way to rate them on different metrics and then assess which ones are on balance, the best ones to steer your resources towards. And the things that we look at potentially are what's the likelihood of success for this problem? What's the likelihood that we'll find a solution to it? What kind of impact might it make to the ecosystem if we do it? So if it's not going to change the bottom line for a customer, we're not going to benefit in a royalty stream from them for coming up with new technology. So we do try to get a balance of, yes, we think it solves real-world problems that people are willing to pay for, problems that we think it's viable that we'll find a solution to, problems that we think the internal research function has the right capabilities to go and research. And then we hope to get output from the projects that we run, and they either feed kind of internally into process developments, or they may influence our partners or the industry at large. Now, kind of along the top line there, you've got research, collaboration, and enablement. So a potential vector is, if we don't think we have the right skill set or the balance of risk-reward is not quite right, perhaps we look externally, we see who the world leaders in an area that we're interested in, but nevertheless not experts in. Perhaps we start partnering with them to see where the technology is going there. So how do we fill this funnel? So you've seen the chart on the left a couple of times already. So death of Moore's law has been called many times. Greg says there's still a bit of life left in it. But nevertheless, the indication and the expectation is that the number of transistors over the years available to new SoC designs is not going to grow significantly through scaling. So you're going to need to look for other tricks to play. So we'll see materials boost that Greg alluded to, and we'll see 3D, certainly. But at the same time, the chart on the right is showing that compared to the perfect scaling, the green line, the cost per transistor is going up, or at least not decreasing as quickly as we'd like it to. And the different lines there are indicative of the effect of the NRE on the number of units that you're shipping. So what does that tell us? It tells you that if you get the volumes, then you can afford to sit on the bleeding edge nodes, and you'll probably be okay. Tells you that, yeah, if you don't have the volumes, but you can mop up a standard platform play, which can then be extensible, again, perhaps you'll get those volumes. But in other places, perhaps you won't. So do you sit back on old nodes and wait for the manufacturing optimization to kick in? Or do you try and make better use of the transistors that you have, be that better architecture, better implementation? So transistors may not be scaling as we'd hoped, but at the same time, the number of devices connected is. These are some classical charts on the left from Ericsson. I think lots of people refer to these ones, showing how the IoT trend is kicking off. And the thought of designing that many systems and making them interoperate and connecting them, maintaining them, making them secure, that's quite scary. Also, the amount of data that they might generate is also very scary. So that tells us a few things, and that leads us onto a charter which broadly defines the areas that the research group in ARM is interested in. So as I said, we're very interested in achieving more with constrained budgets, be that better use of the current process technology that we have, be that revisiting ideas past of different ways of cutting up compute. We see that, given the enormity of the distributed compute system we're talking about, not all of that processing we think will be done in the cloud. You need to spread that to the edges, and you don't want to put that burden on the programmer. So ways to intelligently spread compute to the right place in the system, ways to remove the human from the loop. With that scale, the more manual maintenance that's needed, the more baggage there is. It's not going to scale easily. ML is becoming a ubiquitous tool for the programming community. And we think, again, if you're trying to do some of that processing near the edge, then we're going to need very efficient ML capabilities in energy-constrained environments. Finally, all of these devices connected to open network is just a security wreck waiting to happen. So we're very interested in not piecemeal addressing security, but finding root causes and addressing those in a systematic way. Right, have we got the skill group leads in the house? I can see Eric. So Eric leads Our large-scale systems and software. Have we got Stefan and Matt? Mumble, this is okay. You may need to start looking at people's photos and grabbing them when they turn up. I can see Kanak at the back, who is our internet services lead. So he's interested in techniques to get processing into containers in edge nodes and also smart ways to connect devices and manage them. I guess Matt Horsnell, Eric, Stefan Diestelhaus are all involved in essentially computer architecture related fields. Kanak, as I said, internet services. There's some technologies that we don't know which way is up quite, and that's owned by the emerging technology group, so Gary. So some of the work that Gary's group looked at initially was, say, machine learning. He also has current activity in areas like medical, biotechnology, and also some very novel material opportunities. Gary's group also maintains a disruptive technology roadmap, which is like a ledger of potential technologies that may disrupt the industry, and as I said, a way to rate and score the likely impact and the likely probability that they'll pan out. James, at the back there, leads up our devices, circuits, and systems group, and I think I'd describe that to be, from a given technology, a given process node, how do you best make use of that? So he has great interest in ultra-efficient sensor nodes. Matthew Martina leads up our machine learning group, and he couldn't make it to the summit this year. Do we have anybody from Matthew's team around? A couple of guys at the back there. So again, I'll get onto machine learning in more detail with an example later on. And finally, when everything breaks, it's Hugo's fault. So he leads up our security team. And as I said, we're very interested there in robust architectural definitions to create security guarantees, be they architecture in hardware or in software. And we're also very interested in that group in describing properties of systems and being able to prove something about it. So again, can we describe security properties of a system and from basic principles show that those properties can be adhered to in the system? Okay, so I'll spend a bit of time going through where we think machine learning is panning out. So from big to small, the initial interest has been in the cloud compute, and we're very interested in pushing that out to the edge. So for a number of reasons, be that reducing the traffic going back to the cloud, privacy concerns of sending that data there, or perhaps it may just be the most appropriate energy efficient place to do it. Now, this example is a few years old, but it is indicative of some of the work that the group does. So before we get to propose new architectural extensions, you need to make sure that the thing you're comparing against isn't weak. So at the time, the team was looking at keyword spotting as a example application of the technology, and they were benchmarking current processor cores, making use of the Tensorflow library. I noticed that with the current cores, actually some of the capabilities of those cores weren't being used effectively. So instead of claiming success of, hey, we got 8x speed up with these proposed new instructions that were benchmarking against a weak target, they first did the work to crunch on the TensorFlow implementation, optimize the GemLOP library, and they upstreamed the fruits of that labor. And as a result, you saw Google then be able to pick up the English to Chinese translation on phone rather than referring back to the cloud. So we start off, let's make the current usage of our technology better. We then look to, so that example was using the application profile core. We also have microcontroller cores, and increasingly you see in smartphones system architecture where instead of waking up the big core cluster for every event that happens, you might refer it to a small core first that then discerns, has something interesting happened? Has somebody said the keyword, wake me up? That kind of thing. And based on that information, you might then wake up the big processor cluster. So we ran a project in research a couple of years ago that looked at DSP and machine learning extensions to the Cortex line, kind of proposed those back as a set of architecture extensions, which again would mean that the small core could pick up more work and refer to the big core less often. So once you've done architectural things, you can then get into the implementation. So Mono is a project being led by James's team. And the concept is kind of indicated with the ping pong balls being juggled on the left-hand side. And what James's team saw was there are lots of interesting emerging sensors coming along which consume tens of nanowatts in their active state. And they're kicking out lots of data which needs interpreting. And a lot of the microcontrollers you get will consume milliwatts. So if you're looking at a battery-operated sensor node with this exciting new sensor, and it's battery-powered, you'd like really for the processor interpreting, consuming that data, and maybe waking up a radio to squirt an interesting event back to the cloud, to sip at the battery and not really dominate the consumption. So the mono system architecture is making use of largely off-the-shelf ARM IP, so Cortex M33s, a bunch of GPIOs and controllers and whatnot, but it's partitioned in an interesting way. So you have an always-on domain, which takes activity from sensors and can wake up the processing domain and bring it out of a deep sleep mode to process the data and discern, is there anything interesting happen? Does that need squeezing back over the radio channel? And the block in orange is operating not in full voltage domain, but in sub-threshold. And that comes with some benefits in that you can get extremely low power consumption heading down here. It also means that there is an exponential fall-off in available frequency, but that can be okay. So this is a chart of expected behavior. James claims he's going to beat this, so watch ISSCC papers in the next year or so to see success there. But ultimately, the mono device is aiming to have standby currents of, say, 10 nanowatts, or standby power of 10 nanowatts, and active low-frequency consumption of around 10 microwatts. I have to pick up speed and move on quickly. This is another example of research areas that we're interested in. So listening to Greg yesterday, you saw he had very deep insight indeed in fabrication processes going along in time and heading our way. We have no fabs anywhere on the planet, so we deal extensively with talking to the foundries and also speculating where they're going to go to. So one of the problems we found was we're very interested for our processor designs, where are these deep nanometer technologies going to go? What implications does that have on our processors? And it was hard to get a statement of fact from the foundries ahead of time to influence like the two to 3 year design cycle of processors. So we kicked off a project in research where we speculated on what the future process nodes would look like. And it turns out that Greg and his team were really successful at doing that, in that you could kind of see on the roadmap, so there's either this patterning technology or that patterning technology. What do we think is the likelihood that one or other of those will pan out? And based on that, you can then start getting into, okay, we followed this decision tree. Where has that got us to logically in terms of design rules and implications on the device characteristics? From that, you can start baking spice decks and rolling out hypothetical standard cell libraries that you can then synthesize your cores to and see what the impact of the technology is. So we did some work with Arizona State University to transfer this predictive technology kit flow to them. And we've been collaborating with them to generate standard cell libraries based on hypothetical 7 nanometer technologies and making that available out to academia so they can do their own thought experiments about what these process nodes might imply to people. So this example isn't really about research at all. So I was speaking with Fran Baker from our sustainability group. I was asking for something a bit more appealing than a connected blender or washing machine. And the talking book was brought up by Fran. So I think they have a session after me talking about the ARM's work with the 2030 vision engagement, which is an activity trying to address a bunch of UN goals. So the talking book is an example of, it's actually relatively simple technology. It's an MP3 player, if you think about it, except it takes alkaline cell batteries, which are easy to get anywhere. It's got a really clear to use interface, kind of push buttons on the front, and it has an instruction manual in the local language that it talks out to you when you press the first button. It also has a little USB umbilical cord and a USB socket. So if you find an article, and the articles you get on here are from education to health to how to grow crops more effectively. If you find an article that you like, you can plug the umbilical cord from one to the other and you can copy it. So it's like a book, only better. As Fran was describing this to me, I was scratching my head and thinking, I've heard of this one before. Indeed I did. So I did some scratching around in Amplio. Nobody was mentioned there, but eventually I remembered it. It was something like 10 years or more ago. We were at a review at Michigan University. And after we'd got through all of the programs that ARM was involved with and partly funding, Professor Dave Blau kind of sidled up next to Mike Muller and said, hey, I've got this project that I'm involved with. I'm excited by this talking book, and what I'd like to do is come up with an SoC design specifically for it and make it ultra low power so the batteries last longer. Can I have access to your M0 because I don't want to design one of those? Now, because of the relationship we had with Michigan and the rapport between David and Mike, those wheels were greased and it happened. Ultimately, the custom SoC didn't pan out in the end device. So there were just fundamental startup business issues there of it didn't pan out. But I thought what was interesting was, hey, this looks like a great use of industry-grade ARM IP. Wouldn't it be nice that you didn't have to rely on special relationships with universities or the fact that you know the CTO in order to get things done? So that kind of leads us on to the Research Collaboration and Enablement Program. So that's been recently ramped up, and what that group is aiming to do is to provide a similar model of engagement to the academic community as ARM has for the past 25 years or so with industry. So it's more viewing academia as a customer. You don't pay us quite the same amount, I don't think, as industry will do, but you reward us in other ways. So you'll be doing a whole bunch of non-competitive research that may benefit the industry at large. So the group is led by John, and I'll get on to the other group members in a minute because I think there's some photos coming along. So why collaborate with ARM? So I think for the same reasons that commercial vendors do. So we have proven IP. In their contract with us, when bugs are found, we tend to ship somebody out to their site and work with them until the root cause of the problem is found. We may not do that extensively if there's no license fee being paid from academia, but you probably benefit from already. It's proven IP. It's been incorporated into commercial implementations already, so it should be pretty well baked, pretty well documented. The tools, the platform, the ecosystem is all quality grade. We have, surrounding ARM, one of the appeals for using the technology for industry is that there's a vibrant ecosystem. And again, you can benefit from the tools and the training available there. I guess rattling through this, there's now what used to be in research, more part-time activity and help into academic engagement is now turned into there's a dedicated team there to help you. And I think that's going to make a big difference in terms of the availability and the attention that you get from ARM now. So the group has come up with a funky animation. So I think the purple bars and their height is indicating the number of collaborations that we have going on in any particular geography. And orange is enablement, so provision of ARM IP into universities in that region. And there are a number of ways that we can collaborate with you, kind of enumerated down the right-hand side there. So we work on sponsoring projects and programs in universities directly. We work in the funded research community, so be that in Europe or the US, and we get involved in joint bids into that system. We're members of a number of industrial research consortia, and again through that we have influence in terms of directions we find interesting or providing support and letters of support and the like to universities that are proposing work that we think is strategically important. Then you go through, the potential better research for your money that you may get through, instead of reinventing the wheel, we can get you started with, good quality IP tools and deliver those to you in similar terms that we will be doing to commercial operators. So my hope there is that will get you to a point where you can spend more time on researching your value add and less time spent on building a base control system built around processors and system IP that's needed there. We have another number of activities where we may host researchers inside ARM, and we have an extensive internship program running globally each year. Here's some examples I'll rattle through on collaboration. So we're active, as I said, in a bunch of the funded projects. We're active in 11 of the H2020 projects in Europe. In the UK and Europe, also, we fund centres of excellence. I've picked out Manchester there. We have 4 active in the UK at the minute, so Cambridge, Southampton, Manchester, and Edinburgh. There are 3 others in a pending state. Pending is to be talked about soon, or? Yep, okay. Through our contacts, we've managed to kind of make connections between institutions spanning the Atlantic. So we got involved heavily in the DARPA ERI program, and from that we brought together partners in the US and UK into a software-defined hardware project proposal into ERI. And finally, we're involved in a bunch of the research consortia, so things like SRC. And again, we have many ARM research staff involved in tracking the thrusts going on there and influencing their outcomes. Also from activities like that, we've identified students working for professors that are working in areas that interest us, and we have work that interests them, and from that you pull out some internship opportunities. Then on to enablement. So how does our IP help people? So ranging from many HPC activities through to aerospace and modeling the human brain in Spinnaker, and then making use of ARM IP as a benchmark technology for future process node research at IMEC. So again, I think there are plenty of examples there of quality and actually quite recent ARM IP being used in a more research environment. Okay, so there are more opportunities to speak to the team. They're here in person. So we have Plut somewhere. And Rafaela was standing there, and Andrea somewhere. Is that a hand? I can't see in the... Yeah, you're blinding me. So Andrea's at the back, Rafaela on the side there. So this team is here for the rest of the summit. Please make use of the opportunities if you'd like to talk to them. And there are website things. I guess you will see it on the YouTube if you will for it, or we may hand out the slides later. But anyway, simple URL there, ARMCOM RCE. Finally, I will get onto ARM education. So that was established before RCE and has been running for a number of years now under Khaled. And essentially the focus there is to try and address the perceived growing skills gap between computer engineering and what the industry needs. So Khaled has worked systematically to address a lifelong learning approach through a combination of education kits and online resources and textbooks. I think there was a soundbite from Engineering UK where they're estimating the cost to the UK will be something like 27 billion a year by 2022, based on industry's perceptions of we're going to have to invest this in skilling up graduates coming out of the universities. So the flagship offering is the education kits, and this is a range of teaching materials, so lectures, slide notes, manuals and code, access to the ARM software from ARM and its partnership, and some training workshops and webinars from ARM. And this is available free to educators. I guess this is addressing the university and also more recently the before universities, the schools education. So this is where the education kits sit in. If we then move on to lifetime training, so in industry, continuing on, there are a bunch of more premium online resources available, so lecture videos, lab videos, interactive quizzes with questions, answers, and marking capabilities. And this is more of a subscription-based premium model. Okay, cover that quickly, Khaled, so catch up with Khaled if you want more details. I'm getting close to end of time, so what have I got now? So, I guess at the beginning I spoke about, Arm's success was through partnership, and I think we're going to be pushing more heavily now on, hey, we can partner with academia too. We now have a dedicated group set up for that. Click. There are no end of challenges facing us with, the Pan-out and Moore's law, the explosion of connected devices, security issues concerned there. And working together is a good thing to do. So if we can find ways to work together on these big problems, that would be an awesome thing. So that's coming to the end of my talk about research. I had a little something to say on the Summit PC team. So I won't steal all of Roxana's thunder, as she has a closing pitch to give tomorrow. However, I was really impressed by the work that fundamentally Arm research staff and some friends did in organizing the summit. So it's not like they stopped working since October last year and just focused solely on the summit. They did their day job too. I was impressed by the way they split up their activities and organized themselves. Some people were so busy that I had to hunt them down yesterday. So they're either busy, evasive, or just in the US. But most of all, they squeezed in a lot, had quite a lot of fun. So I won't pick out any individuals there, but there are a couple I will pick out. So there's Roxana, who's the conference chair this year and has done a sterling job. Her enthusiasm and drive and focus has been splendid. And then we have Lucy, who I hear you're called the Summit Czar. So she has brought kind of the organization streak, and I probably wouldn't be stood here today, which may be a good thing or a bad thing, talking to you, because I'd have forgotten when the summit is. So her organization skill has been brilliant. And one thing I'd say, kind of circling back to collaboration, so sitting through some of the PC meetings, probably the most vocal contributors to the process have been these two. And from time to time, they've been not seeing eye to eye, perhaps have differences of opinions. But what really impressed me was, they'd go to the next meeting, and behind the other one's back, they'd be really lauding up the qualities of the other person. So I think, again, that speaks to collaboration. So you can have your differences. It's fine to highlight areas that don't work for you and ways that you'd like things to change. But if fundamentally you've got a bedrock of you have a similar goal, a common goal, you know where you're pulling towards, then you can come up with really good results. So I would like to thank Roxana and Lucy and all of you guys too.